Welcome to International Definition. My name is Kenneth Freelain, and I'm going to be your host for today's edition of International Definition. Today on International Definition, we're going to feature the engineering tribute to the Presidential Inauguration of January 20th, 2013. Today, we're going to receive some information about the North American Water and Power Alliance. The North American Water and Power Alliance was conceived in the 1950s by the United States Army Corps of Engineers. Certain projects were called great projects, and one of the great projects involved the development of more water resources for the United States. The planners envisioned the diversion of water resources from some rivers in Alaska south through Canada by way of the Rocky Mountain Trench and other routes to the United States. And the entire project would involve 369 smaller and separate construction projects. The water would enter the United States through northern Montana. There, the water would be diverted to the headwaters of rivers like the Colorado River and others. The water would generate hydroelectric power as it passed through dams. The water supply would double the total amount of fresh water available to the lower 48 states, with its major focus being on the western states. This would solve the water shortage problems of the West for the foreseeable future. The amount of water available would in fact be so great that some water would be left over for use by Mexico by way of the Colorado River. By the way, today, the Colorado River is significantly depleted as it enters Mexico. The United States Army Corps of Engineers has studied this project in the late 1950s and in the early 1960s. This project was very close to realization. Washington State Senator Scoop Jackson was a significant sponsor. Senator Jackson was a person who believed in this project. The project was opposed by public sentiment in Canada. Recently, there has been a resurgence in the effort to implement NAWAPA, the North American Water and Power Alliance, as a result of the activities of Lyndon LaRouche and his LaRouche Pact. Now, let's watch a video which will provide us with some additional information about this proposed engineering project.
We live on a continent whose western part has a wide discrepancy of rainfall distribution due to the particularities of the Pacific Ocean weather system. The area stretching from Alaska and Yukon down to Washington State has 40 times the annual river runoff of the southwest and northern Mexico. To move some of this runoff to areas where there is little, it appears at first glance that a very long canal or pipeline would be required. Closer inspection shows that such a canal is already built. More specifically, there is a continuous stretch of naturally made canals in the form of Rocky Mountain trenches and valleys, stretching from southeastern Alaska through southern Idaho, roughly 2,000 miles. All that is required is the construction of 31 dams, and a 2,000-mile route utilizing these topographical features can deliver 11% of the runoff water of Alaska, British Columbia, and Yukon, to bring a new source of surface water to the U.S. Southwest and northern Mexico that will last as long as the rain continues to fall in the northern mountains of the continent, an amount capable of doubling food production, saving cities, farms, and industries across the Southwest, and securing the livelihoods for generations to come. The construction of the northern storage and power system will bring with it the independence and industrialization of Alaska, the rapid development of British Columbia, and a general development of the continent as a whole. Implementing the project will save and revive vital industries and technological capabilities, and create millions of long-term productive jobs. Here, we give an in-depth overview of the NAWAPA 21 plan, starting with the 2,000-mile storage reservoir system from Alaska through Idaho. Rainfall in Alaska, Yukon, and BC is about 2,200 million acre-feet a year, and runoff is about 1,300 million acre-feet a year. Of this, the NAWAPA 21 plan proposes to form reservoirs utilizing a group of rivers which discharge 630 million acre-feet a year of runoff into the Arctic and Pacific Oceans. In Alaska, 5 dams utilize 3 major rivers. In Yukon, 2 dams utilize 1 major river. And in British Columbia, 14 dams utilize 6 major rivers. 22% of the runoff of these rivers, or 138 million acre-feet a year, will be utilized for the delivery, pumping, and power generation system, which ends in southern British Columbia. Dams on 1 river in Montana and 3 rivers in Idaho complete the 2,000-mile-long storage reservoir system, delivering 5% of the annual runoff of Alaska, Yukon, and BC into Montana and Idaho to the southwest. We'll now take a closer look at this mountain reservoir system, beginning in Alaska and Yukon. In southeastern Alaska, the Susitna River, with an estimated runoff of 36 million acre-feet a year, flows into Cook Inlet. The Copper River, with an estimated runoff of 46 million acre-feet a year, flows into the Gulf of Alaska, and the Tanana River, with an estimated runoff of 30 million acre-feet a year, begins near the border of Yukon and flows northwest before joining with the Yukon River about 150 miles west of Fairbanks. A reservoir system held at 2,100 feet elevation will be formed in the Copper and Tanana valleys, through 3 dams in the Copper Valley, 2 over 1,000 feet tall, and an approximately 500-foot dam in the Tanana Valley, near the Cathedral Rapids. The 2 reservoirs will be connected with a 30-mile-long tunnel. The creation of these reservoirs will require the relocation of approximately 4,100 residents in the valleys. A dam ranging from 700 to 880 feet tall on the Susitna River will form a reservoir connected to the Copper Reservoir by a tunnel. In Yukon, a 900-foot dam south of Dawson City and a 400-foot dam 35 miles east on the Klondike River will likewise form a reservoir of 2,100 feet, which will connect with the Tanana Reservoir. Power generation by the 7 dams will be roughly 3.5 gigawatts, an increase of 150% for the region. By creating a reservoir on the Yukon River at an elevation of 2,100 feet, a continuous 400-mile reservoir can be formed, which has the same elevation of the Yukon River as it passes by Whitehorse, Yukon, and that of its headwaters at Atlin Lake in northern British Columbia. The southernmost part of the Yukon River Reservoir will meet with a reservoir similarly held at 2,100 feet, formed by a dam on the Taku River, which has an annual runoff of 15 million acre-feet a year. The dam will be over 1,000 feet tall and will be located 60 miles from the mouth of the Taku River on the Pacific. 1 or 2 additional dams of 400 feet will be required to form the Taku River Reservoir. By utilizing 22% of the collected runoff from these rivers, approximately 57 million acre-feet will have been collected. The first pump lift of the system will lift the water out of the Taku River Reservoir into another reservoir held 300 feet higher. The pump lift will be driven by diverting a portion of the 57 million acre-feet a year of water collected to drive turbines through the Taku River Dam, 60 miles from Juneau, Alaska, increasing the annual runoff of the Taku River and generating up to 4.3 gigawatts of power, far above the requirement to pump the majority of the 22% of runoff water up the 300 feet required. The higher reservoir, held at 2,400 feet, will be formed by a dam on the Stikine River, over 1,000 feet tall, and located 130 miles from its mouth in the Pacific. The Stikine River has an annual runoff of 41 million acre-feet. Likewise held at 2,400 feet, a reservoir to the east formed in the Liard River, with an annual runoff of 63 million acre-feet, will connect to the Stikine Reservoir, and will be formed with a dam ranging from 500 to 1,000 feet tall, depending on the needed size of the reservoir. The Stikine Reservoir will connect south to another reservoir held at 2,400 feet, formed by a dam 120 miles up the Nass River, which has an annual runoff of 22 million acre-feet a year. The Nass River Dam will be over 1,000 feet tall, while 4 others in the valley needed to form the 170-mile-long reservoir will average 700 feet tall. The water in Nass Reservoir will flow down into an interconnected reservoir held at 2,330 feet, formed by a dam 170 miles up the Skeena River, over 1,000 feet tall. The Skeena has an annual runoff of 55 million acre-feet. The Skeena Reservoir ends where the reservoir will naturally join with Babine Lake, which sits at an elevation of 2,330 feet. By utilizing 22% of the runoff of these rivers in British Columbia, approximately 40 million acre-feet per year is added to the runoff collected, bringing the total to 97 million acre-feet a year for all the reservoirs formed by these 10 dams in British Columbia and the 7 dams in Alaska and Yukon. After connecting with Babine Lake and Stewart Lake, about 30 miles west of Prince George, the collection will enter a man-made canal and be diverted 2 ways. In the most impressive demonstration of the efficiency of the continental approach, the geological defile, known as the Rocky Mountain Trench, makes it possible to complete the remaining 500 miles of storage reservoirs in the north with only 4 new dams, one dam about 1,000 feet tall at the headwaters of the Fraser River, and 3 other dams averaging 350 feet tall. Of the 97 million acre-feet a year collected, roughly 60 million acre-feet a year will enter a pump lift system beginning 30 miles north of Prince George and be lifted up 670 feet into the Rocky Mountain Trench Reservoir, requiring 6.8 gigawatts of power. The remaining collection not already used for coastal hydropower further north will then drop into the Fraser River, generating power for the pump lift. Inside the trench, 10% of the annual runoff of the Fraser River will be collected at its upper reaches and added to the planned outflow, bringing the total available from the trench reservoir to 72 million acre-feet a year. Under the 1964 Columbia Treaty, the 817-foot Mica Dam was planned and completed in 1972, which already uses 100 miles of the trench as a storage reservoir. The 400-mile expansion of this reservoir will require the relocation of approximately 14,000 residents. The 72 million acre-feet a year collected is to be delivered from the trench into Flathead Lake and Flathead Reservoir, held at an elevation of 2,880 feet, formed by a 400-foot dam in Montana on the Clark Fork River, before transferring through 4 tunnels and 4 mountain reservoirs in Idaho, involving 6 pump lifts totaling 2,450 feet, completing the 2,000-mile reservoir system. The 4 reservoirs are formed by a 400-foot dam on the Clearwater River, 40 miles from its headwaters, an 800-foot dam on the Lochsa River, 45 miles from its confluence with the Clearwater River, an 800-foot dam on the Selway River, 40 miles from its confluence with the Lochsa, and a 1,000-foot dam 160 miles up the Salmon River. The final design for the size of storage reservoirs and location and heights of dams will be made to ensure continuous and steady delivery of water throughout the system, especially during the winter months, and will be determined by the joint assessment of Canadian and U.S. authorities based on the proposed treaty agreements. By preventing a portion of the flow of 4 rivers in Alaska and Yukon, and 6 rivers in northern British Columbia from becoming saline, a permanent renewable source of rainwater will cycle through the inside of the continent, and by effect, greatly augment the runoff of existing rivers in the southwest, tripling available stream flow from 32 to 104 million acre-feet a year, as well as create a new underground river system connecting 30 newly created reservoirs throughout the southwest. Out of the Sawtooth Reservoir at 5,250 feet, a 50-mile-long tunnel through the Sawtooth Mountains emerges into a 640-foot wide, 350-mile-long concrete-lined canal near Littlewood River Reservoir, accommodating a flow rate over twice the average flow of the Snake River. This canal will wind its way through southern Idaho, passing 10 miles from American Falls Reservoir and crossing into the Great Basin just before crossing through the tip of Utah and into Nevada, where a 100-square-mile reservoir will be formed, with a storage capacity of 7.3 million acre-feet, over one-fourth that of Lake Mead. A natural depression between Murdoch Mountain and Bald Eagle Mountain on the border of Utah, 50 miles east of Elko, Nevada, will be filled to an elevation of 5,000 feet. Out of this reservoir, the canal will continue before branching two ways near the city of Trout Creek, Utah. The eastern branch is the central southwest delivery corridor, bringing 48 million acre-feet a year to three basins and northern Mexico, and will begin by connecting with the existing Sevier Bridge Reservoir in Utah and making available 2 million acre-feet a year for irrigation in the area. A canal delivers the water out of Sevier Bridge into a tunnel under the Wasatch Mountain Range, transferring the flow from the Great Basin into the Colorado Basin. The outflow from this tunnel will be into a reservoir between the North Caneville Mesa and the San Rafael Reef, formed by two dams in the Muddy River Valley in south-central Utah, the uppermost near Tomish Butte, and connected to a reservoir between the Caneville Reef and Caneville Mesa, formed by a dam in the Fremont River Valley. The combined storage will be 6.3 million acre-feet, or one-fourth the storage capacity of Lake Powell. Continuing south, the flow will create two more reservoirs in the Capitol Reef Depression and the Escalante River Valley, totaling 1.8 million acre-feet of storage capacity, before crossing Lake Powell via 45 miles of tunnel and siphon and entering Arizona about 20 miles east of Glen Canyon Dam. From here, the main southwest delivery aqueduct connects through a 45-mile tunnel to a large reservoir 40 miles northeast of Flagstaff and 2 miles south of Tuba City, formed by an 800-foot dam on the Little Colorado River. The lake thus formed by a single dam will be roughly 6,000 square miles and average 330 feet deep, yielding a storage capacity of 128 million acre-feet, nearly 5 times the size of Lake Mead. In addition to the main southwest corridor supplied from this central reservoir, a smaller diversion will serve southeastern Arizona and Sonora, tunneling out of Little Colorado Reservoir 45 miles southwest into Oak Creek Canyon, located 5 miles northwest of Sedona, dropping to form a reservoir with a capacity of 1/2 million acre-feet, before continuing through an open canal and meeting with the Verde River, 30 miles from its headwaters. A dam east of Pine Mountain will form Verde Reservoir, held at 3,000 feet, with a storage capacity of 2.4 million acre-feet, alone more than doubling the storage capacity of Arizona's Salt River Project, before exiting Verde Reservoir through a 25-mile tunnel to provide additional water for the Salt River Project's Roosevelt Lake, 80 miles from Phoenix. Where the Big Chino Wash River meets with the Verde River, another tunnel of 50 miles will intersect the mostly dry Hassayampa riverbed, 10 miles north of Wickenburg and 30 miles south of Prescott, creating a reservoir there of 0.7 million acre-feet storage, and another further south down the Hassayampa riverbed. Tunneling west under the Gila River, 3 more reservoirs of 1.3 million acre-feet storage within 50 miles from the border of Sonora will be formed, delivering water for irrigation in southeastern Arizona and crossing into Sonora with an aqueduct, delivering roughly 2 million acre-feet a year. Returning to the main southwest delivery corridor, a lift out of the Little Colorado Reservoir will allow the water to flow by gravity through a series of 5 reservoirs into southeastern Arizona and western New Mexico, before crossing into the Rio Grande Basin. The first is a reservoir at the confluence of the Black and White Rivers, formed by a dam at the headwaters of the Salt River near the junction of Carrizo and Cedar Creeks. The Black River Reservoir will have a storage capacity of 7.2 million acre-feet, over 1/4 the capacity of Lake Mead. Crossing into the Gila River Basin, 2 smaller reservoirs are formed by the Southwest Aqueduct Tunnel and Canal System, each tunnel roughly 15 miles long. The first, formed by a dam on Eagle Creek River, 20 miles from its confluence with the Gila River, and another on the Blue River for a combined storage of 3.4 million acre-feet. Having delivered in total 12 million acre-feet a year of renewable supply to the state of Arizona, providing for the irrigation of 2 million acres without pumping costs, the tunnel system at 5,000 feet continues, crossing into New Mexico and delivering 30 million acre-feet a year. 2 more reservoirs are created in the Gila River Basin. First, on the San Francisco River just east of Brushy Mountain, 30 miles from its confluence with the Gila River, and second with the dam on the Gila itself, 70 miles from its headwaters, located 20 miles northwest of Silver City, New Mexico. The combined storage of the Gila and San Francisco reservoirs will be 21.7 million acre-feet, nearly equivalent to that of Lake Powell, and will divert water south to farms along the river in New Mexico, before continuing south to supply a major aqueduct into Sonora, delivering roughly 7.5 million acre-feet a year to the state, and providing for an increased irrigation of 184%. With the combined reservoirs in Utah, Arizona, and New Mexico, the storage capacity of the Colorado Basin will increase from 61 million acre-feet at present to 174 million acre-feet, nearly tripling. In order to cross the Continental Divide and pass from the Colorado to the Rio Grande Basin, water is pumped out of Gila Reservoir and brought east through a tunnel under the divide, where a large amount is diverted into the Rio Grande River, serving Las Cruces, New Mexico, before continuing south along the border. The rest is routed across the Rio Grande River, pumped a second time, and brought through a tunnel under the Sierra Blanca mountain range, before emptying into the Pecos River Valley, where a large storage reservoir will be formed by a dam on the Pecos River and held at an elevation of 4,000 feet. With its northernmost point being just south of Fort Sumner, and its southern point 30 miles from Roswell, it will be roughly 600 square miles, having a storage capacity of 34.8 million acre-feet, serving as the central distribution reservoir for all irrigation along the Pecos River districts near Roswell and Carlsbad, New Mexico, and the entire length of the river through West Texas, as well as 2 million acre-feet a year pumped north into Colorado. Together with the water diverted from Gila Reservoir into the Rio Grande and from the Pecos Reservoir into the Pecos River, roughly 21 million acre-feet a year will be delivered to Rio Grande Basin's irrigation districts of New Mexico, West Texas, Chihuahua, Coahuila, Nuevo Leon, and Tamaulipas, nearly twice the mean discharge of the Colorado River's 11 million acre-feet a year. Pumping costs will be eliminated, farmland restored, and an estimated 12.5 million acres of crops irrigated, over twice the current total of all the states involved, including the entire state of Texas. Due to utilization of the continental topographic characteristics, the power needed to pump the water along the Southwest Delivery Aqueduct from Little Colorado Reservoir into the Pecos River Reservoir will be generated by the opportunities for gravity flow along the side branches in Arizona and New Mexico, generating a net surplus of power.
I'm glad that you were able to join us for today's edition of International Definition. Today on International Definition, we examine the North American Water and Power Alliance, also known as NAWAPA. We did this as a part of the engineering tribute to the Presidential Inauguration of January 20th, 2013. And now, until our next broadcast, I'm your host, Kenneth Freelain, thanking you for joining us today.